Hello, my name is Cristian Barahona, and for a final project, we have chosen the two methods for training were Siamese networks and contrastive learning. So Siamese networks are one-shot classification paradigm where only a single example is enough for the network to classify images accurately. This network uses the concept of contrastive loss, which finds a pairwise similarity score between the images in the dataset. So instead of learning the contents of the image, this Siamese networks learns the differences and the similarities between them. So this is the structure of the Siamese network. And one of the key features are the Siamese networks utilize share-weights architecture, where identical twin networks process pair inputs, ensuring consistent features extraction while reducing the risk of overfitting. Also, the distinctive design allows them to handle pair or triple inputs during the training, which teaches the network to understand relative similarities rather than just absolute classifications. These networks also quantify similarities between their embedded representations using established metrics like the Euclidean or cosine distance. This provides them a clear mathematical basis for determining how closely the inputs match. And just beyond the theoretical elegance, Siamese networks have been proven remarkably versatile, finding successful applications across domains such as facial recognition, signature verification, natural language processing, and various biometrics authentication systems. Now, the Siamese networks make use of the contrastive loss function, which finds the difference between image pairs by using differences as a similarity measure. This function is useful when there are a few training examples per class. And just a caveat of using this contrastive loss is that it requires pairs of negative and positive trained samples. And we also want to take a look at constructive learning, which is a technique that enhances the performance of vision tags by using the principle of contrasting samples against each other to learn attributes that are common between data classes and attributes that are set apart data class from another.
For our other model, we used a Siamese network, which also leverages contrastive loss sometimes. But in our model, we used binary cross entropy instead. Supervised or self-supervised Siamese models often can be used without labeled data, so it can generate different pairs of positive pairs via data augmentation, and it learns between similar and dissimilar pairs by treating the other augmentations as negatives. It also uses a structured embedding space by focusing on creating these embeddings and then determining which ones are clustered closer together and then improving on spacing out the ones that are dissimilar and making sure that they are separated distance more from each other. It is also very scalable with negative sampling. So as we get more negative samples, we can also increase the diversity and performance of the Siamese structure. The backbone for our models that we used was MobileNet v3. So MobileNet v3 was trained on the ImageNet dataset, not the tiny ImageNet dataset. And the original optimizer used was the root mean squared propagation optimizer, which updates the parameters based on the average of the squared gradients. And then for the torch vision version of the MobileNet, we don't know the exact learning rate, but on the original MobileNet, the learning rate used was 0.1. And for the torch vision model specifically, they used label smoothing, stochastic depth, and learning rate noise injection to improve the accuracy of the model. And they have two versions of the model available. There's the small version and the large version. The difference between them being, of course, that the smaller version has fewer blocks of layers. So for our implementation, we used one Siamese network, and for our other method, we used one contrastive learning model, but that only used two encoders, so two separate encoders. So our Siamese model specifically has two backbone models that are connected together. They have the same weights, and then it uses the MobileNet v3 large as the backbone, and uses binary cross-entropy loss. The contrastive model, on the other hand, uses two separate encoders, but they still share the same weights and architecture. And in this one, we used the MobileNet v3 small because the model was a little bit harder to calculate, so it took a little bit longer. So we had to use a smaller model. Then we also use contrastive loss for the contrastive model. But they both use the Atom optimizer, and they both work by comparing images by the embedding and the distance between the embeddings of the pairs. For our dataset and pre-processing, we use the training of the tiny ImageNet training set. So we used a balanced number of pairs. So we had a balanced number of similar and dissimilar pairs that we generated from the training split of the tiny ImageNet dataset. And then we pre-processed them into the bytes.io library objects, and then use the Python image library to open them up into image objects. And then from these image objects, we process them into torch visions tensors using the basic torch vision transforms, and then resize them into 224 by 224, which is normal for the mobile data input. And then we normalize them to make the model easier to learn.
Now, before diving into the results, we set up a thorough evaluation pipeline. We performed grid search over learning rates of about 0.01 and 0.001 and batch sizes of 64 and 128 to find the best hyperparameters. We also use metrics like training and testing loss, accuracy, and confusion matrices, which were tracked across models. And both the models, Siamese and Contrastive, use the Atom optimizer. And while grid search ran for 3 epochs to quickly assess parameters, the best Siamese model was later fine-tuned for 25 epochs for better performance. Now, looking at the Siamese network results, we observe a clear trend, lower learning rates and larger batch sizes, which consistently help performance. At the same time, training accuracy improved from about 50% to over 80 to 84%, and validation accuracy rose from 43% up to 72%. Validation loss also dropped steadily, highlighting improved model confidence. And this indicates that with careful tuning, Siamese networks can learn fine-grained pairwise relationships effectively. Shifting to the contrastive learning model, we saw very different behavior in this case. Training accuracy stayed lower, around 52 to 54%, but validation accuracy was extremely high, reaching almost 99.7 across all configurations. And while this discrepancy suggests the model found an easy solution that works well for validation pairs, but might not reflect deep semantic understanding. And cell validation loss stayed low and stable, suggesting that the model built a well separated feature space for contrasting inputs. Now, talking about the grid search test accuracy for both the models. Now, when directly comparing the best configurations, the Siamese model achieved about 72% validation accuracy, while the contrastive model dominated with around 99% validation accuracy. The F1 scores and losses also echoed this trend, with contrastive producing near perfect separation. But it's important to recognize while contrastive showed better test metrics, Siamese networks demonstrated more stable learning curves, which is critical for some real-world applications.
Now, when we compare the best models side by side, the Siemens network using a learning rate of 0.01 and a batch size of 128 achieved a valid accuracy of about 72% and an F1 score of 0.83%. Meanwhile, the contrastive model with a learning rate of 0.01 and a batch size of 128 almost touched to 99% accuracy and with F1 score close to 0.99%. Although the contrastive approach clearly outperformed in terms of pure metrics, it's important to remember that the Siemens network is still very effective, especially for tasks reading a fine balance between sensitive and specificity. The next slide. So, looking at the training behavior, the Siemens network required nearly 20 epochs to fully converge, whereas the contrastive model settled much faster, often by around 10 epochs. One interesting observation: while the Siemens network showed a gradual steady loss reduction, the contrastive model loss barely decreased during training. The hints again that the contrastive model found a shortcut for a very simple rule to distinguish pairs rather than deeply learning complex relationships. in the next slide. Finally, on the test set, the Siamese network achieved 96.53% test accuracy with a very low loss of 0.0749, while the contrastive model scored even higher at a 99.32%, but had a slightly higher test loss at a 0.2503. This suggests that while contrastive learning achieved the highest accuracy, Siamese network offered tighter, more calibrated predictions with fewer extreme errors. So next slide. In conclusion, both methods proved powerful. The Siamese network excelled at careful and stable learning of pairwise relationships, while the contrastive model leveraged aggressive separation strategies to dominate metrics. Each has its strengths. Siamese networks are extremely useful when interpretability and sample efficiency are key, whereas contrastive learning shines in scaling and maximizing classification margins. Ultimately, the choice depends on the specific need of the application. Thank you.